Okay, let me resume the lecture. So we defined plane partitions, and yeah, it is an array of integers that are inside a Young diagram. There is another way to represent this, graphical, like a Young diagram of a partition. You can think of this as a three-dimensional partition in this way. So graphical representation of plane partition. So our plane partition looks like this. Okay. And now I'm gonna stack boxes so that in this corner we will have 3 boxes stacked in a pile, and 2 boxes to the right, left. Let me draw, you will understand what that means. So it's gonna be like 3 boxes and 2 boxes, 2 boxes, and 2 here, and 1. See, like a little drawing session. Okay, see, we have 3 boxes stacked in a pile like this, and 2 boxes too. It's quite useful if you write the number of boxes at the top of each pile. You can see 3, 2, 2 boxes, 2, 1 boxes, like that. So this kind of stack of boxes is a graphical representation of this partition. Okay, basically we arranged boxes in this XYZ coordinate, the positive octant. I just put boxes first here, and then so basically I first put boxes here, and then another one here, another one here for this first stack, and etc. So one other box here, and then here, etc. So that's how I constructed this box. Okay. Now, one way to understand this. Another one. Now, just consider these boxes. So some boxes are visible, but some boxes are not. But you know which boxes are there or not. Just give coordinate to each box. So, for instance, this one will have coordinate 1, 1, 1. And this one will have coordinate 1, 1, 2. And this one at the top will have coordinate 1, 1, 3. Okay? So pi can be understood as a set of coordinates. So 1, 1, 1, 1, 1, 2, 1, 1, 3 for these first 3 boxes in a step. And for this, what is this? Can you tell me the box coordinate of this box at the bottom of this? 1, 2, 1. And for this, 1, 2, 2. And for this, what is the coordinate for this? 1, 3, 1, 1, 3, 2. And for this box, 2, 1, 1, 2, 1, 2, and this 2, 2, 1, like this. Okay? So we can think of this as a set of coordinates. Of course, the coordinates have to satisfy certain condition. Alright? Now I'm gonna define B of A, B, C is the A times B times C box, meaning something like this. Here we have A boxes here. The length is A, length is B, length is C. So it's C. Something like that. Okay? So this is a plane partition. It's a rectangular shape. I'm going to use this notation for this box. Okay? I told you that the generating function for all plane partitions has a nice product formula. And there is even more interesting thing. The generating function for plane partitions inside this box also has a very nice product formula. Okay? Generating function. Okay. Yeah, maybe I have to define this first. Generating function. What is the generating function? When you have a sequence, the generating function for sequence is quite obvious. So A1, maybe A0, A1, A2, dot, dot, dot. It's a sequence. Sequence of numbers, let's say. Then the generating function for this sequence is actually I will tell you in more details about this generating function next week, but let's just give you the idea. Is this an, xn, and from 0 to infinity. So x is the just formal variable, but usually we use q, so let's use q here. In this class, we will often use q as a variable for the generating function. Okay, the generating function is it's very simple actually. This is not just one way of recording this sequence. You can just imagine if you have this generating function, you can read off each coefficient, right? That will give you the nth number in your sequence. So it's one way to record this sequence. But what's nice about this generating function is that we can think of this as a formal power series, and then we can apply the many operations in formal power series, such as addition, subtraction, multiplication, or derivative, something like that. So it's a very useful tool. It gives us a connection between combinatorics and analysis. And this for sequence is like that. So the generating function for the number of plane partitions is like this. So this is the generating function for the number of plane partitions. But if you remember, I just said generating function for partitions. What does that mean? Partition is not a number, it's just an object. But when I say generating function for some object, combinatorial object, it means that for each object we add something, some monomial. That's basically the idea. So it's not a very formal and concise definition, but you can see the generating function, maybe a generating function, not the unique, a generating function for some object, I don't know, some combinatorial object. So you can consider permutations or partitions, plane partition, anything like that. A generating function for object means a formal power of series object, say in S. So S is a set of objects. Okay, objects. Something like this. For object, say pi in S, we add something. I don't know, a of pi, a sub. Yeah. It can be. It can vary each time. Sometimes we add. So, for instance, So lambda partition Q to the lambda. You can see here, for each partition lambda, we added something, some monomial. This kind of thing is called a generating function for some object. So I will often use this terminology. Generating function for partitions, generating function for plane partition, something like that. So by choosing this quantity, you can have different generating function. So usually we say generating function for partitions according to their sizes, or generating function for partitions. So we even have more variables like this. So this is a generating function for partitions that follows not only size but also length. This kind of the series is called a generating function. So this is the generating function for the sequence of plane partitions, but you can also think of this as a generating function for partitions, because maybe pi is a plane partitions, I don't know, all plane partitions Q to the side. These are equal. So this is a generating function for plane partition, something like that. Next week we will learn more about generating functions, but this is basically the idea. Are there more questions? Okay, now I can say the generating function for plane partitions has a nice product formula, right? And now we restrict ourselves to generate plane partitions inside a given box, A times B times C box. And the generating function for all plane partitions inside this box, can you imagine this generating function? Okay. So my claim is that, or statement, the generating function for plane partitions inside B, A, comma, B, comma, C. So this is a box of side length A, B, and C. Is so I didn't really specify what this quantity is, but usually it means the size. So pi is a generating function, plane partition inside box. That I will just write something like this. That means we can think of plane partition as a set of coordinates, right? So it is a set. So as a set, it is a subset of this, which is also a set of coordinates. Q to the. So this is what I mean by the generating function for plane partitions inside this box. We add plane partitions inside it. So this is not a infinite power series. It is a polynomial indeed, right? Because we have finite terms here. There are only finitely many plane partitions inside a given box, because the box size is also finite. There are only finitely many plane partitions. Okay? Can you imagine this plane partition? I mean the generating function. Just imagine just a bunch of all plane partitions. Okay, they are just listed in some way, and then you add Q to the size of that. Okay. Maybe example: A equals 2, B equals 1. Just very simple example. Let's look at this. So what is B? It is this, right? B 2, 1, 1 is this, right? So how many plane partitions are there that are contained in this box? How many? 2? 2 or 3? 2. Raise your hand if you think there are 2 plane partitions. 3, 4, 0 or else. Empty set is also a plane partition. So there are 3. Okay? So pi can be empty or just one box or B itself. There are 3 plane partitions like this. Okay? So for each plane partition, we add this q to the length or size. Q to the size is 1, 2. So it's going to be 1 plus q squared. This is a generating function for plane partitions inside this box. So this is the same. There are only just much more partitions there. Just think of them as listed in some way. You just add monomial to each plane partition. Okay? That's the definition of this generating function. So if A, B, C are like infinity, we have infinite size box, then we can consider all plane partitions if A, B, C are infinity. Okay? But now they are fixed. Okay. So the question is, don't we need integers inside boxes? Actually, there are the original definition of a plane partition, which was lost, was a filling of integers inside a Young diagram. But we represented this as a box, real box like this. So this one, actually what this means is 1, 1. So because we already expressed this as a stack of boxes, we don't need numbers anymore. So actually, when I wrote numbers here, it's only for the helpful visualization. You don't need these numbers. Okay, just stack of boxes represents plane partition. More questions? Okay, now we know this definition, the generating function for plane partition. The thing is, it also has a very nice product formula. That's called MacMahon box theorem. Those of you who have seen the movie called The Man Who Saw the Infinity, 무한대를 본 남자. It was a movie about Ramanujan. If you have seen this movie, you may remember there was a character whose name was MacMahon. He was a very famous professor at that time, and he was one of the founders of algebraic combinatorics, one can say. His book titled Combinatorial Theory that was published more than 100 years ago, but there are still people who refer that book. And MacMahon was maybe the first one who considered plane partitions, I think. Yeah, but maybe I'm wrong. So he was interested in this object, and he had many interesting results. So this is a generating function for plane partitions inside this box, and it has also nice product formula like this. Alright? This is the theorem due to MacMahon. Okay, let's check just for fun. A equals, because we have already computed this. Let's compute the right hand side. We knew that it was this, right? Left hand side, J is always 1, K is always 1, I is either 1 or 2. If I equals 1, okay. Just step by step, let's do this step by step. I, J, K are both 1, so it's gonna be plus 1, just like this. So I equals 1, we had 1 minus q squared. 1 minus q, 1 minus q cubed. Is this right? Yeah, that's right. So we can cancel this, and you see these are they are the same. So it works, at least for this very simple case. But this is true in general, and yeah, very nice theorem. And as a homework, we will. So this is more general than the generating function for plane partitions, because if you let A, B, C approach infinity, we get all plane partitions. And as a homework problem, you will solve. This implies the generating function for all plane partitions. That's not a difficult problem. You can think about that later. So of course, it's also not an easy theorem. So we will prove this later on. Any question about this? All right. Now we have learned plane partitions, and we learned that there are nice product formula for their generating function. All plane partitions or plane partition inside the box. But what's interesting is that there are more there are more structures in this plane partition. Okay, it's about symmetries in plane partition. So let's just consider partitions first, because they are simpler. Lambda equals 4, 3, 1 partition, and there is a very natural operation on this partition. Young diagram, especially when you have a Young diagram. Transpose. A transpose of lambda is what you imagine. Just reflect this diagram along this diagonal line. So you will get 3 boxes. So rows become columns and columns become rows. Okay? If you flip this along this line, you will get this. Transpose. Very natural. So the definition, lambda is symmetric or self-conjugate. This is also called conjugate. They mean the same thing. Symmetric or sometimes called self-conjugate if lambda is equal to the transpose of lambda. So this is not symmetric partition. So example, maybe this is an example. Okay, this is an example of a symmetric symmetric partition. If you take the complement, you don't change anything. It's just it stays the same. It's a symmetric partition. Oh yeah, I'm gonna just tell you the result. Actually, it's not very difficult, but maybe we will prove this later. So, generating function for symmetric plane partitions. What does that mean? You list all symmetric plane partition. There are infinitely many, and for each symmetric plane partition, you add q to the size of that plane partition. So, that symmetric partition. Symmetric partition. So this is the generating function for all symmetric partitions, right? And it also has a nice product formula as there was for just all partitions. Okay. It has a nice product formula. Proof is not very difficult. You can prove this as an exercise. So yeah, even though we impose some symmetry there, we still have nice product. Plane partitions, we have also symmetries. So to do that, let me define So plane partition we write as an array of numbers like this. Transpose is obviously defined, can be defined here. The transpose is what? You reflect this along this diagram, or this line. So 4, 4, 4, 2, 1 will be a first column, 4, 3, 2, like this. Okay? Then you can define symmetric plane partition. Pi is symmetric if pi is equal to pi, let's write it in this way, transpose. This is pi transpose. So example, pi 4, 3, 2, 4. This is a symmetric plane partition. Reflect is the same. And as a diagram of boxes, you will see something like this. I just want you to have some image how it looks. It looks something like this. Okay, you see, it's symmetric along this thing, right? They are symmetric, like decalcomany. So pi is symmetric as a set. So you know we have three different ways to represent plane partition, like an array of integers, or stack of boxes, or set of coordinates. So pi is symmetric if it satisfies this condition. This is in pi if and only if. Can you tell me what coordinate we should have here? Yeah, I and j are changed. So if you have something here, you must have the same this box there as well. So it's a they're all equivalent. So this is the definition of a symmetric plane partition. What's interesting is that there are more symmetries because we have three-dimensional object in this graphical representation. We can consider more symmetry. Okay. I think I need to, because it takes too much time for me to draw this. I'm going to show you using the lecture note. Course information here. Lecture notes. By the way, this is a slide that I used in a summer school last year, so I'm not going to cover everything in this slide, so most of this. Oh yeah, here. So cyclic. So we have defined symmetric plane partition. We have another symmetry called cyclically symmetric. So the idea is this: if ij, k is in pi, this is equivalent to saying that j, k, I. So we cyclically rotate these coordinates. So of course these are the same. They're equivalent. So plane partition is called cyclically symmetric if it satisfies this condition. Alright? So this is an example of a cyclically symmetric plane partition. And you can understand this as follows. You rotate this diagram 120 degree counterclock or clockwise, then you get the same thing, same picture. That's the definition. You can think of this as the definition of a cyclically symmetric plane partition as well. Okay? rotate this 120, you get the same thing. So this, if this box is there, this box must be there, this box must be there, etc. If this is there, this box is there, then there. Okay, you see? It's a beautiful picture. Alright, now let me go back to this. Yeah. So you have already seen the picture, so let me just pi, let me rewrite this again. Cyclically symmetric if I, j, k in pi, if and only if j, k, I, pi. If this is true, then it is called cyclically symmetric. Alright, now it is also called, there's another symmetry. Actually, is intersection of two symmetries. So pi is called totally symmetric if it is both symmetric and cyclically symmetric. This is the definition of a totally symmetric plane partition. Totally symmetric means, so in this diagram, if you reflect along this horizontal line, you get the same thing. If you rotate 120, you get the same thing. Then it's called a plane, totally symmetric plane partition. Any question about these symmetries? Okay, now I'm gonna tell you this very interesting fact. They all have very nice formula. So number of, I'm going to just tell you just number of, this is plane partitions. A, B, C, this means, just for now, number of plane partitions inside B, A, B, C. Okay? If I write this, it means just that. So the number of plane partitions inside A, B, C, nice formula. Yeah, let me just write this for real quick. It has a product formula like this. We even had generating function, and if you set Q approaches to 1, you will get this. So this is basically a consequence of MacMahon's box theorem. What's interesting is that we learned 3 more classes of partitions, plane partitions: symmetric plane partitions, cyclically symmetric plane partitions, and totally symmetric plane partition. They all have nice product. Yeah, nice product. I'm not going to write this. It's something like this. Slightly more complicated, but still nice. You can read the textbook or lecture notes for this. Oh, by the way, can you see why I wrote AA instead of AB? Yeah, they have to be the same. But here, if it's cyclically symmetric, the box must be the same. Also nice. Doesn't mean that they are the same, but nice. Totally symmetric plane partition, also nice. They all have nice product. This one is especially nice, so let me write this. Very nice. They all have small prime numbers and has simple formula like this. So some history. So this is due to MacMahon. Yeah, more than 100 years ago. This one was conjectured by MacMahon, proved by Andrews. George Andrews, very famous number theorist, and especially in partitions, 1979. And MacDonald, also very famous mathematician in symmetric function. Cyclically, this is about this. For cyclically symmetric, conjectured by MacMahon, MacDonald, 1978, proved by Andrews, the same year. And this one, conjectured by MacDonald, proved by maybe around the same year, Stanbridge, 1995. So they're all proved. So you will see a little more about another kind of plane partition. Again, I need to have this lecture notes. Yeah, here. It's called descending plane partition. But before doing this, how can I? Okay, let's just go for now. Okay, let's review cyclically symmetric plane partition again. So here we have a cyclically symmetric plane partition. Oh, no. Okay. Now I'm gonna decompose this into what's called shell. So outer shell is like this. So it is the set of boxes with coordinate, one of the coordinates being 1. Okay. It is like that. And then remove this box. Remove this first layer, and then do the same thing. Then from here, we just consider boxes with coordinate, one of the coordinates equal to 2, and we will get this. The second layer or shell. The third shell will be just this box. All right. And because it has very nice symmetry, cyclically symmetric plane partition, we don't need all the boxes here. Only just one partition or one part will be enough to recover the whole thing. So instead of having all of this, let me just consider the bottom boxes, and then put it over here. And then for here, again, consider the bottom boxes, put it over here. But shift this like this, so that they are in the same relative order as in this previous partition. And again, for this, just put it over here. Okay? This is enough. This has enough information to recover this, and of course this. This is in fact a bijection. We only need to specify some conditions on what these are. Okay? Now, if you look at each floor, it is a Young diagram. So it is a partition. Okay? So let me write this as a partition. So how many boxes are there? 1, 2, 3, 4, 5, 6. 6, 5, 5, 4, 3, 3. I write them, those numbers here. And for the second floor, 3, 2, 2. 3, 2, 2, but shift it to the right by 1. And 1 box over here. So the array of numbers obtained in this way is called, this kind of array is called a shifted plane partition, because the integers are shifted to the right each row. And we have to have this condition. This is a shifted plane partition, but strict. That means if you go down, it has to be decreasing, strictly decreasing. can you have a 5 and say 5 and 5 here? Do you think you can have 5 and 5? No, we cannot. Why? Yeah, because this can reach at most over here. In that case, it will be only 4. But because we have removed one box here, this is always smaller than the number of boxes below. So this is always bigger than this. These are always strict, like that. So strict plane partition. So shifted means shifted like this. Strict means strict along each column. And we have one more additional condition, which is each row, the largest part is equal to the length of the row. So what is the largest part in this row? 6. What is the length of this row, or the number of parts here? 6. 1, 2, 3, 4, 5, 6. 6 is equal to the number of parts. 3 is equal to the number of parts. 1 is equal to the number of parts. We must have this condition. Why? This, if you shift this or rotate this 120 degree, you have to have this. You have to match with this. So this must be equal to the number of boxes, like for every floor. So we must have this. And actually, these are enough information. These are enough conditions for this array. So in fact, cyclically symmetric plane partitions are in bijection with this kind of arrays. All right. So if you want to compute the number of CSPP, you can instead compute the number of such arrays, because it's easier to write down. It always takes a lot of time to write this. We just extracted essential information. Okay, let me rewrite this in this lecture note. So cyclically symmetric plane partition can be identified with a sequence like this. So it's a shifted, strict. So here we must have weakly decreasing each row, but strictly decreasing each column. That's what this strict means. Such that in each row, largest part equals number of parts. 6 equals number of parts in that row. Okay? George Andrews proved the formula for the number of cyclically symmetric plane partitions using this observation. So using this, Andrews proved the formula for CSPP, number of CSPPs inside the box. His proof is very complicated. He interpreted this as a determinant, and he evaluated the determinant, but it's very complicated. Yeah. We are not going to see his proof. But he defined something highly unmotivated. Let me tell you. Don't ask that question because it's not really motivated. A descending plane partition. Yeah, but I like this story. Very interesting. Descending plane partition. What is this? Is a strict shifted PP plane partition, just PP for short, such that, so see, we have this condition for cyclically symmetric plane partition. We have a different condition, such that largest part of row I plus 1 less than equal to the row length of row, or this is a row length, number of parts means row length of row ith row, and this is strictly less than largest part in row I. Okay, quite long condition. And dpp of n is the number of descending plane partitions with largest element less than or equal to n. So this is the definition of a descending plane partition. Okay? So, why did he consider this? He considered this because he invented his method to compute this. But he realized that if you change this condition a little bit, because he understands this proof very well, oh yeah, if you change this condition a little bit, we have a different object, but we can still enumerate this. That's why he considered this. How do you think? Very unmotivated. Usually this kind of the people will say, that's not that's just for definition for, I don't know, to write a paper. I don't know. Very unmotivated. The only motivation is, like I said, because it works. Because his method works here. But there is a very interesting story here. Let's compute this for just to get the idea. Example. dpp of 3 equals 7. Because it can be 0, empty, or 2, 3, 3, 1, 3, 2. You can check the condition, guys. Yes. It satisfies this. Okay. And theorem, he computed this. Andrews. Oh yeah, before stating this. Yeah, I should have mentioned this earlier, but the number of alternating sign matrices, this was conjectured by 3 physicists, Robbins, Ramsey, I forgot the name. Do you remember? Yeah, Robbins, Mills, and Ramsey. They couldn't prove this, so they asked the expert on this area, who was Richard Stanley, the author of the enumerative combinatorics. He's a very famous combinatorialist, mathematician. So nowadays, when we have a sequence, we search on the internet. It's called OEIS, Online Encyclopedia of Integer Sequences. You just type in your numbers, sequence of numbers. It will tell you which known objects match with your numbers. So you can say, oh yeah, maybe they have the same number. There must be some very close connection. But by that time, they didn't have any kind of encyclopedia. Richard Stanley was kind of that person to connect people using his database in his brain, meaning his brain or his notes. So these 3 physicists, they asked Richard Stanley. Stanley couldn't prove this conjecture, but he realized that, oh yeah, I have seen these sequences from Andrews' paper. It was this. So the dpp of n, what Andrews proved was this. J from 0 to n minus 1, 3j. Can you recognize this number? 1, 2, 7, 42, 4, 29. Etc. Stanley realized that the number of alternating sign matrices, n by n, are equal to these numbers. So Stanley told them, "Oh yeah, I've seen this sequence in Andrew's paper, so you should look at this paper." So obviously they have looked Andrew's paper. So yeah, this is a theorem. This seems to be the same as this is conjecture, right? AN, alternating sign matrix. If you want to show this, all you need to do is to find the bijection between this and alternating sign matrices. Nobody has done it so far. Finding a bijection between DTPP and alternating sign matrices is still open. It's wide open. No one has any progress on this so far. That's a very interesting story. There's one more interesting object. There is one more symmetry in plane partition that I didn't tell you yet. Any questions so far, by the way? There are more symmetries. One more symmetry that we missed. Symmetry in plane partition. So we know with two operations, transpose and cyclic shift. If it's invariant on the transpose, it's called symmetric. If it's invariant on the cyclic shift, it's called cyclically symmetric. If it's invariant on the both of these operations, it's called totally symmetric. There is one more thing. If you look at just the box, the enclosing box together, another operation, complementation. So, example, pi is this plane partition that I showed you earlier. Like this. Just for helpful visualization, I'm going to write these numbers. Number of boxes. 0 here. There's no box in this step. This is inside this box 2, 3, 3, which is like this. Okay, this is contained in this box. All right. Now, B2, 3, 3 minus pi. Let's remove boxes in pi from B. What you get, but yeah, let me redraw this diagram. Okay, you would get something like this. You will get this part, right? And let me write numbers over here. How many boxes are left here in this card stack? 1, right? Because 2 boxes are removed. How about here? 2. Here? How many boxes are left in this box, in this stack? 1. Here? 3. So we draw this so that we have maybe we have to 3, 2, 1, something like that. I'm gonna just redraw this as to be a real plane partition. 3, 2, 1, 1, 1, 0. 3, 2, 1, 1, 1, 0. Basically, it's just subtracting these numbers from 3. This is called the complementation. You see, this, if you do this, you get another partition, also plane partition, also inside this box. So it is an operation on plane partitions inside a given box. Another operation. So now we can have more symmetries. Are you okay with this definition? More symmetries. Pi is self-complementary if pi is equal to pi, let's say C was complement of pi. All right. We assume that the outer box is given. That's without the outer box, we don't really have complementation. So, and pi is called transitive transitive complement if pi transpose equals pi C. Yeah, so you can combine this, but you will realize at the end there are 10 different symmetries in plane partitions inside the box, inside the box of the same side length, n, because otherwise we don't have. Oh yeah. Okay. So 1, plane partition with no restrictions. All right. 2, cyclic symmetric plane partition, AAC. Cyclically symmetric. Oh yeah, I think I can just show you this diagram because I want to show you the diagram. There are 10 different symmetries like this. So here, plane partitions with no restriction. Cyclically symmetric, cyclically symmetric, totally symmetric. We have seen these 4 already. Now, self-complementary. Transpose complement plane partition. Symmetric self-complementary plane partition, meaning it is symmetric self-complementary. Cyclically symmetric transpose complement plane partition. Cyclically symmetric self-complementary plane partition. Finally, totally symmetric self-complementary plane partition. TSSCPP. This is very famous. So totally symmetric self-complementary. So it is not only totally symmetric, also self-complementary. It has all possible symmetries that you can give. This is an example of TSSCPP. If you do any operation, including self-complement, complement, you will get the same thing. Rotate, flip, any direction, complement, the same thing. It has the most, everything. It has every symmetry, TSSCPP. And they all have nice product formula. This is the history and when they proved. And for the TSSCPP, it has to be 2n because otherwise you cannot have symmetry. It's 0. 2n, 2n, 2n. The number of totally symmetric self-complementary plane partitions inside 2n by 2n by 2n box is equal to this. It should be 0. Can you recognize this number? The number of alternating sign matrices, n by n. So, number of alternating sign matrices, number of descending plane partitions, number of TSSCPPs, they all have the same numbers. but no one has found bijections between any two of them. But they are all proven that they have the same number. These are history. This is an example. Okay. They all have nice product formulas. You can read the book. Okay, let me do one more slide over here. Yeah. So finally, so even though people came up with different objects with the same same number, no one was able to prove this. But finally, Zeilberger proved the ASM conjecture. But his proof is not. His proof was very, very complicated. So ASM, there are many different combinatorial objects, or some of them are quite equivalent. There are many combinatorial objects that are counted by ASM. One of them is monotone triangle. We will come across to this object later. But this one-to-one correspondence is quite simple. So this is almost the same as ASM. You can think of that. And he defined what's called Markov triangle. And TSSCPP, we will see in this semester, there is a nice correspondence between this and non-intersecting lattice path. And this is a one-to-one correspondence between some kind of non-intersecting lattice path. And there is also a simple bijection between this and Markov triangle. And then what Zeilberger showed is that this number of monotone triangles is equal to the number of Markov triangles. And because we know that this is equal to that product formula, it has a link from here to that formula. So that gives the proof. But his proof, so mainly his contribution is the proof of this, inventing this terminology and definition and this. But his proof was very, very complicated. This is his proof. The proof was 71 page long, and he couldn't find any. So I visited his webpage. He had wrote down this story. He first submitted this paper to a very prestigious journal, like Journal of AMS, but the journal didn't want to. The journal didn't accept this because they couldn't find a referee to review this paper. Too long, and I only show this first part of the first page, but inside this paper there are many sub-lemmas, like sub-lemma, something like that. So no one was willing to spend his or her time to review all of the details. So what he did was he found referees by himself. He contacted combinatorialists and other mathematicians. Would you please review just this part and this part, etc. So he invited 88 reviewers, and these are the number of reviewers. You can see many people like Noga Alon, he's a very famous graph theorist, George Andrews, even anonymous. Maybe, let's see, Richard Stanley, Robbins, Mills, Ramsey, maybe. But anyway, there are very famous mathematicians here. They all check the details. So now it was published in Electronic Journal of Combinatorics, and yeah, people say that this is the first proof of ASM conjecture. So it is now a theorem, but very difficult and hard to read. But fortunately, shortly later, after his proof, Kupperberg, he's doing mathematical physics, found a shorter proof using statistical mechanics. There were enough materials developed already in physics, theoretical physics. So Kupperberg realized that these can be applied to prove ASM conjecture. So he finally proved this. It was quite short, like 16 pages. So we will hopefully learn his proof in this semester. Maybe at the end of the semester we will be able to, if this lecture is successful, we will be able to see his proof. He uses many interesting things. So this is basically the history of how the ASM conjecture was proved. And in this semester, we will go over these details, the many objects like plane partitions, symmetric functions. Plane partitions have very close connection with symmetric functions, and also hypergeometric series, which is a very useful tool to prove identities, and also a statistical mechanics model. I'm not going to go over the details, but you can read this paper, this slide, or lecture notes, or monotone triangle, and square ice. Just for a short note, square ice is something like this. So ice, a water molecule has one oxygen and two hydrogen, two O, one O and two H's like this. They are connected like this. And O's are arranged like this, H's are arranged like this, but one O want to have two H's. And the number of ways to connect, the way to connect O's and H's to have molecules, or water molecules, there is a simple connection between this and ASM, alternating sign matrices. And that's why physicists consider ASM. And we will learn this later in this semester. So we will learn all of this, and hopefully at the end of the day you will appreciate the beauty of the theories in alternating sign matrices. It's not just about combinatorics, but also about many other areas in mathematics. Now, nowadays, 2 or 3 or more areas in mathematics are joined together to have some results. Combinatorics is one of the areas that has this kind of features. Many problems in different areas can be formulated as a combinatorial problem. So combinatorics, if you learn combinatorics, you may be able to attack some problems that you haven't been able to do this. So this is the overview of this semester, and the homework, you will need to submit homework to, next week 9 a.m. right here. Any question? Okay, thank you for your attention, and I will see you next week.